Professor Brooks is a professor in the Department of Computer Science and actually joined USF in 2002 after completing his PhD in computer science from the University of Michigan. He also holds an MS in computer science from San Francisco State University and a BA and a journalism BA in English and journalism from the University of Wisconsin. So Professor Brooks' research examines the way in which humans and computational agents learn in shared environments, particularly when it's difficult and costly. He also develops new techniques for effective teaching of computer science and AI, and is deeply interested in addressing the issues at the nexus of social justice and computing. And with that, I am going to share my screen and present his research video. Give me just one moment until I find it. Actually, I'm realizing. Okay, I'll do it in a second. Can I call them in a second? Awesome, thank you. Sorry about that. ITS is trying to help out with my wireless. Let me actually unshare because I didn't press share audio. That would help all of you. Sorry for the clunkiness this morning, folks.
So today I'm going to talk to you a little bit about some work that I've done in multi-agent learning over the years, both before my time at USF and then also with students here at USF. So let me start by apologizing for not being there to do this synchronously with you. I'd originally intended to do this as a synchronous lecture, but unfortunately I had a scheduling conflict, and so I'm really sorry that I can't be there. But I hope this video does a nice job of letting you know the sorts of things I've been working on. So before we begin, let's talk a little bit about what the idea of an agent is, for those of you who don't have an AI background.
So I just got a message that the video stopped. Can someone confirm, either unmute yourself or message me in the chat and say that you could or could not hear it? I'm using my phone's Wi-Fi, so I apologize. Good morning.
Yeah, I couldn't hear it, Jen.
Oh, okay. Could you hear it at the beginning?
I could hear in the beginning, but then it just paused.
I'm gonna try hitting play again. I don't know why it's doing that. I apologize. I've not had this issue before.
As well, and learning is really the core part that I was interested in.
Awesome.
And in AI, when we talk about learning, what we mean specifically is this idea that an agent can improve its performance on a task over a period of time. So in other words, if it was able to classify images at 70% accuracy today, and then tomorrow at 80% accuracy, we would say that it learned to do that task. It improved its performance. In order to do that, it might need to acquire some knowledge, it might need to experience the world, or it might need to gather some evidence of some sort. And so when we talk about a learning problem in the AI world, it can have a lot of different characteristics. We're trying to do it. And so what about multi-agent problems?
Sorry, I was muting the mic
so
you wouldn't hear the wind,
just really has to do a single agent, where it's our agent against the world. Then what if we start to introduce other actors into the scenario? So in a multi-agent problem, you have more than one agent, and it might be some humans and some computers, or all computer agents, and they're all trying to learn at the same time. And this makes the problem even more complex in a couple ways. The first is that now we need to model each other. If it's just our agent out in the world, even if the world is non-deterministic, we can still use probability largely to treat it as what we call a stochastic environment. That is, behaviors don't always go the way we want, but the world is more or less randomized. When there are other agents in the world, we can't really do that anymore. Now we need to think about how my behaviors will affect the way you see the world and what it is you're trying to accomplish. Because you have intentionality and you're making choices in order to do something. You're not just a random process. And so I need to think about the agent in that way. The other problem is that it makes the learning problem non-stationary. What I mean by that is this. In a traditional machine learning problem, as our agent gathers data, what it's trying to learn doesn't change. In other words, if I'm trying to learn to classify pictures of a cat, what a cat is doesn't change during that learning problem. It stays static. Well, in a multi-agent learning problem, what I'm trying to do, what my best choice is going to depend on what you're doing. And what your best choice is going to depend on what I'm doing. And so if we're both changing our behaviors because we're learning, well, our past knowledge maybe is not that valuable. And so we need to be mindful of that and throw away old data that may not be meaningful anymore. So that makes it even trickier for us. So there's lots of different ways that a machine learning problem in a multi-agent environment can happen. There's lots of different ways in which these agents could be either learning about or with each other. In some cases, it's cooperative. You have a number of agents that are all built by the same person or the same team, and usually for environmental reasons, they're distributed. So maybe it's a robotic soccer game, and your robots are trying to learn how to execute a pass or play defense. A more real-world example would be search and rescue or logistics, where you have a number of agents that are out in the field deployed, and they're trying to share information and give updates to each other, and they're geographically distributed so that they can cover more territory. So in that case, they're on the same side, and the problems become about coordination and sharing information and updating each other's models of the world. We could also have a purely competitive environment where every agent in the mix is self-interested, but yet they need to interact in some way. They're often buying or selling things, for example, in an automated market. Or we can think of autonomous vehicles driving on the road. Each one needs to get to its own destination, but they still need to cooperate with each other and not get into accidents and obey the rules of the road. This sort of setup is widely used in things like Amazon's cloud provisioning as well, to set prices and allocate resources as demand changes. And then in some environments, some of the most interesting ones are both. Our agents might still be self-interested, but there's opportunities for them to collaborate with each other and share information. So for example, we might have an environment where our agents are all delivering packages from one place to another. And even though each agent is trying to maximize its own utility, it's trying to deliver its own packages as quickly as possible, it may be in both of their best interests to switch packages. If all my deliveries are in San Francisco, except for one that's in Oakland, and all your deliveries are in the East Bay, except for one that happens to be in Daly City, if we could meet someplace and swap packages, we're both better off, even though we're self-interested. Robotic exploration is another example there where each robot has its own utility function and its own area of, let's say, the surface of Mars that it needs to explore. But by sharing their plans and coordinating and eliminating redundant steps, both can be better off. So my own research, I was really interested in this question of how agents, either computational or human, can discover each other in complex worlds where learning is expensive. And so where I first got involved with this, back when I was in grad school, was in an economic setting. And what we were interested there was finding out how producers and consumers of information goods could find each other and how they could establish efficient markets. Now, information goods are digital. So you can think of that as a digital book or an MP3 or a movie. What's interesting about them, they have a few weird things that make them not behave like traditional economic goods, like a bushel of wheat or a bin of iron. A big one about them is they have what's called zero marginal cost. So what that means is that the first copy of something is very expensive to produce. So Avengers Endgame costs $350 million to make. And so you can say that to create that first DVD or that first Blu-ray or whatever of Avengers Endgame, that costs $350 million. The second one costs zero, essentially. Once it's done, to make more copies of that movie is trivial. That's different than, say, a car, where making the first car has a fixed cost, and making the second car still has a significant marginal cost associated to it. Most physical goods behave that way, and so as a result, there's a point where the producer, it's not in their interest to make any more cars. There's not enough people who want to buy them. Information goods don't have that same characteristic because they have this zero marginal cost. And so once I've made that first copy of Avengers Endgame, it's in my best interest to make as many copies as I can because it doesn't cost me anymore, as long as I can find somebody to buy them. And so that leads to some weird behaviors when you look at it from an economic perspective. There's a lot of tendencies towards monopolization and towards having one producer that just sells kind of the most mass market things. So what we're interested in is finding out, are there ways around this? Are there other outcomes, other mechanisms that we could create that rather than just leading to this monopolistic behavior where there's one seller, who, Amazon basically, can different sellers find their own niches in the market so that different people with different kinds of preferences can find the information goods that they want more easily? And we're really interested in this concept of bundling and how it is that maybe producers and consumers compete on other things besides price. Since price had this weird marginal cost behavior, what if instead I can make my decisions around other things, like the kind of content I want to sell? And if I can find content that particular niches in the consumer market are really interested in, and I can figure out how to bundle that content together, in other words, pair together things that seem related. So people who like Sci-Fi Network might also like Cartoon Network, for example. If I can discover what those bundles are, maybe I can add value that way, and that'll allow multiple producers to thrive and avoid this sort of cutthroat competition that you get with a monopoly. Now, if the world was static and the consumers were just holding still and they were willing to tell you what they liked, then it's not so hard. The producer could just try different things and see what people bought and see what they didn't buy. But it's not static because both producers, or however many producers you have in your world, are all learning at the same time. And so the best thing for me to offer depends not only on what the consumers are, what they purchase, but it also depends on what the other producers are offering at the same time. And so our question was really, how can you structure this problem so that when it's in the producer's best interest to not compete, but to instead identify separate niches in the market, focus on those, how can we structure that problem so that they can discover that solution? So that Star Wars fans and WWE fans can both find the content they want. Producers are incentivized so that one will cater to Star Wars fans and one will cater to wrestling fans. So theoretically, it turns out it's not that hard to solve. And so a lot of this work was done in collaboration with some economists, where they solved the closed form analytical solution. We're able to show that there's what we would call Nash equilibrium. In other words, with perfect information, the producers should figure this out. I'll sell Star Wars, you'll sell wrestling, and everything is great. The question came up, when does that happen in practice when you're letting agents learn these things? Can they converge on the equilibrium if they don't start out with perfect knowledge? And what we found in these settings was that the cost of learning was really important because learning is expensive. The producers want to maximize their total profit over time. Okay, and so if I choose a complex model, well, I might eventually converge on the right solution, but it might take me a lot longer because I might make a lot of mistakes along the way. And what we found was that choosing different models for how to price your goods in other words, different models of what you thought the consumer's preferences might look like, made the learning problem easier or harder. And so, because the landscape is what we would call rugged. If you look at this picture here on the left, it shows a number of different pricing schemes. And you can see, for example, the red line has a lot of peaks, what we would call optima on it, that a learner, especially a hill climbing learner, is going to get stuck on. On the other hand, you have maybe this green line here, which doesn't hit the same peaks in terms of profit, but it's much easier to learn because it's much smoother. And so it turns out that our learner is able to exploit that smoothness and converge on an optimum much more quickly. This right-hand picture here shows a 3D version of the same phenomenon, and you can see that the grayscale areas show different plateaus that a learner is going to get stuck on. And so even though there is a Nash equilibrium there where both producers will find the right solution, it's tough for the two of them to find it because the landscape is has a lot of discontinuities in it. And so the take home there is that if the learner is able to reason about the model that is trying to solve and the difficulty of learning that model, it can trade off long-term reward versus learning cost and solve the right problem in a way to maximize its profit. Once I got here to USF, I got the chance to work with a lot of really cool students. And with one of them, we started to look into a version of this problem called the prisoner's dilemma. And if you've probably heard of the prisoner's dilemma before, it's a very famous problem in game theory. And it's interesting because it's got some really frustrating behavior. What we see here on the left is what's called the normal form representation of the prisoner's dilemma. And essentially the way it works is like this. You have two players, A and B. And player A is represented over here with the columns, and player B is represented with the rows. The game is symmetric, so it doesn't really matter which one's which. And the idea is this. If both players are willing to cooperate, both will receive a reward of 3 if they're willing to work together. If player A defects and player B cooperates, well, then player A is going to get a reward of 5, and player B gets a reward of 0. Likewise, if player A defects, but player B cooperates, player A gets a reward of 5, and B gets the reward of 0. Now, if they both defect, they both get a reward of 1. Now, in this case, we're assuming the agents are completely selfish. All they're interested in doing is maximizing their own profit. Well, in that case, we as humans look at this and we say, oh, they should pick 3-3. They should cooperate together. Of course, that's a really good outcome. The problem is this. Remember, each agent is able to reflect on the other agent, and in the economic setting, they have what we call perfect information. In other words, agent A knows that agent B is aware of all this information and is doing the same calculation. And so agent B says, you know what, if agent A is cooperating, I should defect. Because if he's cooperating and I defect, I'll get 5 and he gets 0. And 5 is way better than 3. So I'm going to do that. But agent B is engaging in that same reflection. It says, if he's going to cooperate, I should defect. Because 5 is better than 0. And what's more, if he's defecting, I should defect. Because 1 is better than 0. If he's going to defect on me, I should defect on him too. And so you wind up with both agents choosing to defect and winding up in this state. This is what we call the Nash equilibrium state for this game, where they each receive 1. But this is a really frustrating outcome to look at when you step back a little bit, even though their logic makes total sense. Defecting is what we call the dominant strategy. No matter what my opponent does, if I defect, I'll do better. But if they would both just cooperate, they would both do better than that. This game came around in the 50s. It was introduced by John Nash. And it's interesting because it seems to apply to a lot of foreign policy and real-life situations. It was applied to nuclear non-proliferation for a long time, with the idea being that both countries, the US and the USSR, would be better off if neither one pursued an aggressive military posture and built up nuclear weapons. But yet they both seem to be driven into this arms race by going through this same reasoning. So how do you escape this? How do we get out of it in real life? Because we cooperate with each other all the time. Well, there's 2 ways that it happens. One is that in real life, we have social norms. That is, rules and expectations and behaviors that govern the way we live our lives. If we go around betraying everybody and defecting all the time, we're going to get treated badly. We might get arrested, we might get shunned. Things will happen to us that we don't like. And so we have some other incentives built into the game. There's another way that we can escape the prisoner's dilemma that's maybe a little more quantitatively appealing, which is we can use what's called iterated play. The idea here is now we're not going to play the prisoner's dilemma once. Instead, we're going to play it lots of times against lots of different players. And we're going to see what strategies win out. And so rather than starting with an analytical approach as Nash did, this is an experiment that was originally set up by Robert Axelrod, who's a political scientist at the University of Michigan. And so he set up an experiment in which he invited people from around the world to create their own prisoner's dilemma strategies, and he would have a tournament. And so everybody submitted strategies. And what happened was, so now you've got this large pool of random strategies, and you let them play against each other. In the work we did here, we implemented this using an evolutionary approach, and so we encoded them as a genetic algorithm. And then those strategies that are more successful continue on, and those strategies that are less successful tend to die out. So you insert some randomness in there, either by probabilistically selecting more fit individuals, or by injecting mutation and crossover to create new individuals so that you can get some diversity back into your population. And you let it run over and over. And so over time, the more fit strategies tend to win out, and the less fit strategies tend to die off. And what you see, what Axelrod found, and what a lot of people found afterwards, is that the strategy called tit for tat turns out to work really well. Even though analytically you can't prove that this is a dominant strategy, you can't prove it leads to Nash equilibrium, in practice, when you simulate it, you find that tit for tat wins against almost every other distribution of strategies in a population. And tit for tat is a really easy strategy. A lot of people came up with these really complex schemes and ways to signal, but tit for tat works really straightforwardly. All it says is start by cooperating. And after that, whatever you did to me last time is what I'm going to do to you. So if you defected on me last time, well, then I'm going to defect on you. And then I'll just wait and see if maybe you switch back. Maybe that was a mistake, or maybe you're just a defector. And if you're just a defector, then, as we saw before, the best thing for me to do is also defect. But if you're switching around and you're experimenting, well then, after I punish you once by defecting, if you're willing to cooperate again, then I'll trust you again and we'll cooperate again. And so tit for tat works really great. It's very simple. And again, it seems to win out against a broad array of other strategies. You can handle people who are aggressive, and it works well with cooperators. This approach is also a nice example of a different way to do science. It was one of the first places where you saw a third way, in addition to doing an analytical approach like we would see in the game theory that I discussed before, or a purely experimental approach like you would see in, say, a lot of biology and chemistry, is a simulation-driven approach where there was not a natural phenomena being observed, but instead there's a computer simulation of an environment that was created and studied. And so now you have this third way to really ask scientific questions. So what my student Colin and I did was we said, well, one thing about the prisoner's dilemma is that it assumes everybody's going to play against everybody. And it assumes that I can remember who I played against before. So I can always identify you, and I can always say, oh, you defected or you cooperated. And I'm uniformly likely to play with everybody. But real life, that's not how our world works. In the real world, we live in what's called a small world network. And a small world network is, if you look at this figure down on the lower left here, and this is from an article in Nature by Duncan Watts and Peter Sturgotz. What it shows here is, this is what's, you've probably heard of 6 degrees of separation, that concept that we're all connected to everybody else in the world by 6 hops. And, people will play the Kevin Bacon game. The goal there is connect Kevin Bacon to any other movie actor in 6 steps or less. The phenomenon behind that is this idea that if you imagine human connections as a network, Most of us have very few connections, relatively speaking. We maybe have on the order of 10 or 20 friends, but then there's a few people who are mega connected, movie stars, athletes, politicians, people like that, who have tons and tons of contacts. And in networking terms, we would say they have a very high out degree and a very high in degree. Your normal person has a relatively small degree. But because you have these largely connected nodes in your network, you're able to hop between different relatively isolated subgroups pretty easily. So you can construct a small world network by taking a regular network like this, where everybody's connected to their neighbors. In this case, this is one with degree 2. You can see this one is connected to their neighbors to the left and right. And then you start rewiring it. You delete some of these edges at random, and you add in some edges across the network at random. And so what you wind up with is you get some people like this here. This fellow is not only connected to his neighbors nearby, but he's got this connection off to this whole other part of the graph. And so what this gives you is a mathematical model of that phenomenon that I was talking about in the real world, where most of us have relatively localized connections of friends, and then maybe we leap off into one or two other friend groups, and those groups are all pretty tightly connected. They're a clique, but then they connect off into another group as well. And you've got those people who are just, they're the connectors. They bring all the different groups together. So if you built a network like that and asked people to play the prisoner's dilemma on that, would tit for tat still work? Would that make sense? What would we find out about that? And so my former student Colin and I worked on this. And we used a genetic algorithm here again, similar to what Axelrod had done, to encode different strategies and played out in some different graphs. It was a really interesting experiment. What we found out at the end that I found exciting and interesting was that having more neighborhoods in the graph, that is building a graph that's got, that's not random like this. When it's completely random, then what happens is defectors can kind of hide in the population. But when you can construct a network that's got a lot of clicks in it, and it's got a lot of opportunity for people to play against their neighbors and build a community, cooperation emerges, which kind of makes sense, right? That's a result that you would hope to see based on what we see in the real world. When people are able to build a relationship and build trust, then they're going to cooperate with each other. And when people are able to sort of slip around and interact with strangers all the time, then defection becomes more tempting. Later on, I moved on to work on some other projects with students at USF. One of them that we worked on was building a system that would allow users to collaboratively discover and tag research papers. The idea was like this, that you as a user are browsing the web and you're looking for some research papers that look interesting to you. And you find something that looks cool, but you don't want to stop right then and bookmark it and kind of follow the rabbit hole down to learn more about it. You're busy doing other things. So you just push a button on your browser and you annotate it. And then our agent would go out on the web automatically and crawl a set of databases and look for other papers that seem to fit your interests. And we do this by inducing some tags from the paper. And a tag is just a keyword that describes the content of the paper. And then it would also look at your friends and compare your profiles to your friends' profiles and look for similarities. Here's papers that your friends have read who seem to have similar interests as you and have used similar sets of tags. And part of the puzzle there was not only learning a user's profile, which we did through some fairly standard IR techniques. IR is information retrieval, but also kind of agreeing on what the meaning of tags were. Because as you probably know, if you've used tags at all, there's not a fixed vocabulary. So for example, I could use the word spam as a tag to indicate that I thought something was an email that I didn't want. You might use the word spam as a tag to indicate a delicious spiced ham that you like to eat. But we mean different things by that. So what we wanted to do was try to eliminate some of that ambiguity and suggest a consistent set of tags so that if you're using, say, for example, the phrase neural networks to tag a paper, then I would want to also have that tag recommended to me, as opposed to say, NNs or neural nets, which are different phrases. So in that way, we wanted to kind of reduce our tag vocabulary and make it easier for users to share data. And then, so this is a paper that was published with some students back in 2006. We then extended that to another interesting piece of work where we wanted to auto-tag blog entries. At the time, blogs were still really big and hip. And so the idea was that we wanted to be able to take a blog entry, automatically extract tags from it, and do that same recommending of, here's the tags we think you should apply, but then use those tags to construct a hierarchy. The other challenge with tags is there's sort of a flat information space, right? So if you see, for example, so what we did was we used what's called a hierarchical clustering method to build a tree out of them. Because again, as I said, the tags are flat space. And so you don't have this concept of more general and more specific, right? So for example, I might have over here gardens and gardening and garden ponds, and then wine and cheese. And we found that there was a relationship between articles that were tagged with one and articles that were tagged with the other. They shared a lot of keywords, they shared a lot of similarity, because they were both sort of talking about, sort of home topics, kind of bed, bath, and beyond sorts of things, as opposed to health or insurance or politics up here. And so we were able to construct what we would call a taxonomy, just completely inducing it from the ground up, starting with the document contents, doing TF-IDF, for those of you who've been in my AI class. It was a very similar version to what you did for your homework. Then comparing the vectors with cosine similarity to identify documents that were more similar than others, and building hierarchical clusters out of those. And then, so this is work that I did with a former student, Nancy Montañez, and that we presented at a conference, WWW 2006. After that, I took a detour and spent some time in the dean's office. And so now that I'm back in the department, I've been getting my research program back up and running and trying to figure out what I want to do with myself. And currently I have two big things that I'm really interested in. The first is I'm very interested and have been working on this for a long time, developing pedagogical tools to help people teach AI and help students better learn AI. I believe pretty strongly that you learn best by doing, and that coding out an AI algorithm is a really great way to understand it well. There's currently a lot of tutorials out there for different off-the-shelf toolkits, and there's some real toy data sets, but I feel like there's sort of a gap in the middle where students can sit down and learn to code an algorithm, build it themselves relatively easily, and really apply it on an interesting problem set. And so I'm really interested in creating more of those things and then creating the scaffolding that helps professors deploy in their class. I'm also very interested in applying AI concepts and techniques to problems that have any sort of social justice or humanitarian component. That is using AI to either address a social justice problem or deal with some issue involving poverty and global justice. So if you're interested in those things, or you want more information, or if you've got any questions, please feel free to email me here at cbrooks@usfca.edu. Again, I'm sorry that I can't be there in person to talk with you about all this stuff, but I hope this is interesting for you, and I look forward to talking to some of you soon. Thanks a lot.
Okay, folks, that was the presentation. You can see two live classmates. Sorry. Anyways, thank you so much for joining us. I will post the video if you want to get the omitted volume. Thank you for letting me know that every time I muted myself, it muted you. But thank you so much. Next week is Thanksgiving, so we will not be having a research seminar next week, but we will the following week with Professor Hayden Lee. Have a wonderful day, and hello from USF.